All right. So I would like to introduce Kasimir, who is a security researcher. He does vulnerabilities at Trellix, and he's going to be talking to us about how to escape the tar pit and secure your supply chain.
Thank you. So, as he said, welcome to Escaping the Tar Pit and Securing the Supply Chain. Thank you, everyone, for showing up after hotel checkout. All right, so let's go ahead and get started. Who am I? I am Kasimir Schulz. I'm a security researcher over at Trellix. If you want to contact me about this research, other research, or just in general, you can just contact me at kasimir.schulz@trellix.com or my Twitter, which is abraxas7331. I would also like to give a shout out to Charles McFarland, who is a researcher at Trellix who helped me a lot with this research. All right, well, let's go ahead and get started. So before we can get to the fun stuff, the patching and the in-scale GitHub work, we actually need to talk about what exactly is the tar file vulnerability. And before I go into what it is and how to exploit it, I'm going to give you a bit of history about the vulnerability. So the vulnerability was first discovered in 2007. And so I just want to reiterate, it was an N day, it was not a 0 day I discovered. And despite being discovered in 2007, there was not really any discussion on how to mitigate this vulnerability until 2014. In 2014, we started seeing some discussions on GitHub. However, the discussions were more focused on whether or not this vulnerability should even be fixed rather than how it should be fixed. And because of that, we don't really see much action on it until 2018 when a pull request was submitted. However, in 2019, that pull request was, in the end, not merged because of failing test cases and some other issues as well. Then in 2021, somebody refiled the issue, and then after no response came in 2022, they re-reported the bug. All right, so what exactly is CVE 2007-4559? Or from now on, I'm going to refer to it as tar file because that's just a mouthful. Nobody wants to say that. So the CVE is actually a path traversal attack in the extract and the extract all functions in Python's tar file module. So the tar file module is actually part of CPython, so it is built in and part of every single Python installation that you have. And then the way that the vulnerability works is there's extraction on file metadata that has no validation. What you actually see up here on the screen is the vulnerable piece of code within the Python tar file code. And this is actually a snippet of code from the extract function. The extract all function actually uses the extract function as well. And as I outlined here, we have the os.path.join on the path and then the tar info.name. Path is the path that you are trying to extract your file to, and then tar info.name is just the piece of metadata from the file. So that's where the file name, and that's where you can actually add whatever you need to use for the path traversal. So let's talk about actual exploitation. What you see here on the screen is actually the piece of code that you need to exploit the tar file module. And as you can see, it's pretty quickly and easily created. And most funnily, it's actually, you can use the tar file module itself to exploit the tar file module. So as you can see here, we have a little piece of code. We import the tar file module. We have a function called change name, and then we open a new file called exploit.tar, and then we add our malicious file. So the malicious file can be whatever you want to overwrite, since we have path traversal leading to a file write, which you can then use to exploit whatever project. And what you see that might be a little bit special here is we have the filter, and that filter calls a function called change name. This is part of the tar file module. It allows you to add a filter that you can then change metadata with. And as we can see here in the change name function, we add the .. which is how we do path traversal. So the malicious file is not going to be actually opened up in the directory you want, but rather in the parent directory of that. And that can get pretty bad going forward. So now that we've talked about the vulnerability, but let's talk about the scale of the vulnerability, since obviously we need to talk about the scale so that we can figure out why we actually had to patch. So some of these numbers might look a bit confusing. Some of you actually might recognize some of these numbers. The 1,000 is the search result limit for GitHub. So if you've ever tried to search code on GitHub, you've probably seen that after 1,000 search results, it says, I'm not giving you any more, which is not great if you're trying to patch everything, right? Or even just trying to figure out what exactly is vulnerable. However, we saw on the side that there were about 300,000 code results for this vulnerability. So we saw that there were around 300,000 files that contained the tar file module, since that is what we were looking for. So we actually contacted GitHub, and we're trying to work with them for this vulnerability to find out the true scale of the vulnerability. And I woke up one morning with an email from GitHub and a several gigabyte file, which was quite surprising since I was expecting about 300,000 file names and repos. And we discovered that there's actually 2.87 million files on GitHub that import the tar file module, which is pretty big. And then we did a bunch of work, a bunch of deduping that information, and we discovered that there's around 588,000 unique repositories that import the tar file module. So that's 588,000 files that we had to search through. And obviously, no one wants to do that by hand. I am definitely a lazy person, and if I can, I will automate, which I'm betting most of you will as well. So we decided to build a tool, or just have a tool to do that. And this is actually how I built Creosote. So Creosote is the tool that we built in order to actually scan for this vulnerability in code bases. And then later on, I actually modified Creosote to do the automated patching, which I'll talk about later in the talk. So let's go ahead and talk about the requirements. So what did we need Creosote to do? So we needed an automatic way to scan vulnerabilities over millions of files, right? Because we had millions and millions of files. We also needed to have confidence levels attached to each result to filter out what manually needed to be looked through. Because obviously some pieces of code are going to be more likely to be vulnerable while others aren't. And nobody wants to look through every single potential vulnerability. You want to have marked which ones to look at, which ones maybe you look at if you have time, and then also depending on what type of work you need to do. For example, security researchers might only care about vulnerabilities that are most likely vulnerabilities. Well, if you're trying to patch your code base and make sure there's no more vulnerabilities, you're going to look at everything, even the false positives. And then finally, we needed a way of receiving a report that pointed directly at the vulnerable line of code. Because obviously, just telling you a repo is vulnerable isn't going to do much. You can start looking through there, but you still have to do a lot of work, which the tool should do. And as I mentioned earlier, I'm pretty lazy. So the first thing I decided to do was try to find another tool that did what we needed. And I came across a tool called Bandit. Bandit's actually a pretty popular tool, and I bet a fair number of you use it, but for those of you that don't know, it's a tool that's designed to find common security issues in Python code. So exactly what we needed to do, right? So the way that Bandit works is it processes each file, builds an abstract syntax tree from it, and then runs appropriate plugins against the abstract syntax tree nodes. So those plugins are actually plugins that you create, so you can easily create your own plugins and find vulnerabilities that you discovered in other code bases using Bandit. And once Bandit has finished scanning all the files, it generates a report for you, and that report can be modified via the plugins as well, which is pretty much everything that we thought we needed. So we tried using the tool to actually write some stuff, and we realized, oops, we can't use it. Otherwise, we wouldn't have generated our own tool. So there were two main reasons why we couldn't actually use Bandit. The first was that Bandit looks for a specific node. So it looks for an attribute node or a call node. And then after that, you can do your check. However, with the Python tar file vulnerability, which I'll talk about later, we have multiple different nodes that then lead to the vulnerability. So to go down, you would have to do a lot of extra work. And with Creosote, we were actually able to bypass that work by checking at a specific node and then backtracing back to check the other nodes, which was a lot more efficient. And that brings us to our second point of we had to actually hack at the functionality of Bandit to be able to look backwards, and that's something that we just didn't want to do. And the reason for that is actually because the way that Python abstract syntax trees work is parents isn't automatically on the node, which I'll talk about how we bypass that later. So then once we saw how other tools did it, we saw what we needed to do, and we updated our requirements. So we added a new requirement that we needed to add backtracing to figure out the context of the archive extraction. It wasn't enough to know that we had an archive extraction. We had to know if the code actually does try to do any checks on it, or if there's anything else done. So before we can get to the really fun stuff that you guys are all here for, I'm going to give you guys a bit of background on abstract syntax trees, especially abstract syntax trees in Python, especially for those of you that may not have used them before, or if you just need a quick refresher. I know a lot of times, I'll know a topic and then I'll forget about it as I go. So for those of you that haven't worked with abstract syntax trees before, the way it's set up is you have a simple, if you have something like this is an expression in Python. We have 2 times 7 plus 4. So obviously, we need some way to represent that in an abstract way. And the way that abstract syntax trees would work for this is you have binary operations. So you have the left node, right node, just like a binary tree. And then you have the operand. So for this one, since there are 2 different operands in here, we have to figure out what we're going to do there. So for our tree, we're first going to have the plus, which means that on the left-hand node, we're going to have another node. And then on the right-hand node, we're going to have the 4. So as you can see here on the left-hand side, we have another node that's another binary operation, and then on the left we just have the constant, and then from there we also have 2 and 7. So that's just a high-level overview of how abstract syntax trees work, and let's actually talk about how they work in Python now, because that's a bit different, and obviously there's going to be different specifications and weird tweaks for the code base. So in Python, we have these major groups that I'm actually going to go through and talk about a little bit, but the way that the nodes are split up are into these 7 major components, or sorry, 6 major components. And before I continue there, I would like to give a shout out to greentreesnakes.readthedocs.io. It is an incredible site that actually has a lot more detail about how all the nodes work, and the Python documentation actually references this site and says, hey, if you actually want more information, go here. They did a lot better than us, which was actually pretty nice to see that they actually gave a shout out to them as well. All right, so let's go ahead and get working here. So most of you have probably worked with literals. You see what those are. So you have the constant and num, string, list, tuple, and then the one that I can't say the shortcut for because I'm on air, but dictionary. And then let's actually go through and discuss how these nodes work in Python. So obviously with a constant, you need some way to store the value. And the constant node is going to have a value attribute which holds the Python object it represents. So for our example earlier where we had the node with 4, that is a constant. And then if you have dot value, that would actually be the value of 4. As you can probably guess, with constants, the values can only be primitive types. So you have numbers, strings, and then the none type as well. Next, we have variables, which I don't even have to explain to you how important variables are, especially when you're doing source code analysis, right? So the most important component of the variable that the node holds is the name. That is stored in the attribute for .id. And then what's also really interesting is that it stores the context. And for those of you that may have worked with Python bytecode, you might recognize load, store, and delete. It's not too important for this talk, but it was important enough that I wanted to give it a shout out during going through this. Python bytecode has different ways that it handles variables. So you can load a variable, you can store a variable, all of that. And when you actually have the abstract syntax tree nodes, you can actually see exactly how that's handled. So if you are working on something else that's using the Python abstract syntax tree, it is actually very useful if you need to do that sort of analysis. Next, we have expressions. For our expression, the 2 times 7 plus 4 would be a good example of the first expression since we didn't return it or do anything or sign it. So it would appear as a statement, but it is truly still an expression. And then, as you saw earlier, we had the binary op, where we have the op, which contains the operator, and then we have the left and right nodes. And then most importantly, for Creosote itself, we have the attribute node. So the attribute node is important because you have a value, which is another node, but you have the .attr, so attr, which is a string giving the name of the attribute. For our example, we have tarfile.extractAll. So .extractAll, that extractAll component would be the .attr, so that is why that is a very important node. Next up, we have our statements. For our statements, you probably recognize most of these. We have assign, we have import. All of you probably realize that import might be important when we're trying to figure out which files, import tar file. And these are pretty simple. You have just targets on assign, which tells you the list of nodes. And then once again, you have your value, which tells you the actual value that it's set to. And then import, we have a list of names that are then used for the aliases. Next up, we have control flow. And for this slide, the ones that are actually important to us are for and with, and I know you're probably wondering why they're at the bottom then. That's because the if statement actually does a bit of some weird stuff, and that's, if you've ever worked with Python, you've definitely used elif, right? And the way that the if statement works for the control flow in the abstract syntax node is there is no body for elif. So you have your body and you have your or else, which both contain a list of nodes. And it's important to note that those nodes are in order of the source code appearance. So when you have your if statement, you have a block of code. Everything that's in there is then is a node in the body or else. And then the elif is actually another if node within the body. So that's how that works. It's just a little thing, but it is fairly important and can be frustrating when you're trying to build a tool and all of a sudden, parts are missing. So for us, the important components are the for and the with node. For for, once again, we have our targets attribute, which contains all the variables that the loop assigns to. We have iter, which contains the item for the that's going to be looped over. And then once again, we have the body or else. some of you might be wondering why for has or else, and that's actually because in Python, you can actually have an else statement on your for loop, which when you're trying to do source code analysis and you don't know things like that can be fairly interesting. So definitely had some mistakes happen there. We also have our with statement, which has an items of with nodes. And the way that with statements work, for those of you that may not be too familiar with that, is you have a code block. So you have the with statement, which opens up a context. And then you have an indented code block that uses that context, and then that context automatically closes afterwards. So for example, opening a file, the file is automatically opened as soon as you leave the indent. And then finally, we have our function and class definitions. These are pretty self-explanatory, so I'm not going to go too in-depth with these. Function def is defining a function, and class def is the class definition as well. So then now we can actually get to the interesting components. So in order to actually write a tool that scans for vulnerabilities, you need to actually know what you need to look for. And for our case, we had two major formats for this vulnerability. We had what we called the extract all vulnerability, which is when the tar file gets opened in a with statement, and then after opening, the tar file is extracted using extract all within the first block, or the indented block. And then the second major vulnerability that we saw was what we dubbed the extract in a for loop, or the for loop extract. And we loop through the get members function, which is a function for tar file objects. And what it does is it gives you all the files within the archive. And the way that that works is during the for loop, we run through and extract and run extract on each object. Together, these two vulnerabilities constituted about 90% of the vulnerabilities, or even just vulnerable lines of code that we saw. And that's a pretty large number, especially since it's two very, very specific examples. So you might be wondering, you know, how does that happen? And that's because in almost every single tutorial that we saw, and I mean really almost every single tutorial, even on Python's documentation itself, Stack Overflow, Geeks for Geeks, Tutorial Point, every single one actually shows you how to extract the tar file incorrectly. So it will extract, but it is vulnerable. So it's just something to keep in mind when you're using a site like that for something else. So that is why we saw the same, which was actually great for us because we only had to really code for those two specific vulnerabilities. So now that we know about what we're checking for, let's talk about the internals of the vulnerability. I'm going to slow down a bit so that we can actually really talk about this. So the first thing that Creosote does is when you run it, you give it a directory to scan. Our directories were just, we had all the repositories in one major directory, and then we just pointed it at that directory and let it go because we wanted to let it run overnight or over a few days, more over a few days, and I'll talk about that later. But the way that it works is it takes the directory and it recursively goes through all the files in the directory that you're given. Once it finds all the files, it goes through and it sorts all the py files, and we use glob and iglob for that. And then it looks for anything that imports the tar file module. The reason for that is because there is a fair amount of overhead turning source code into an abstract syntax stream, and sorting through all the Python files first, and then all the files that only include the tar file meant that we only had to run our code analysis on the files that might actually be vulnerable. And we actually did not use the abstract syntax tree to find the import, and the reason for that was because that would have been a good amount of overhead turning something into an abstract syntax tree, but we used string scanning, and the reason why it was so fast was because imports are almost always going to be at the top of the file, so the string was going to be found very, very quickly, because normally, you know, just scanning the first string is not very quick. So once we actually found all the files that contained tar file, we actually wanted to start scanning them. So what we did was we started feeding the source code to our analyzer class. And the analyzer class was just an abstracted class that is provided by the tar file, or by the abstract syntax tree module, and it's a node visitor. So if you've ever worked with abstract syntax trees before, you have all the different types of nodes, and the node visitors allow you to create abstract functions, so override functions, and then for each node. So if you want to visit the attribute node, you'd override the visit attribute node, and then anytime that it sees an attribute class, you just go into there. From our analyzer class, then turned the source code into an abstract syntax tree. Then it walked through the tree and added the parents to each node. So this was the important step I mentioned earlier for how we could add backtracing. And the reason for that was because the nodes by default do not have a parent node attached to them. However, when you initially walk through a tree, the function that does the walking has the parent and the current node, so you can then attach the parent back to the node and then reference it later on. And then from there, we started actually visiting the nodes. And then, so as I mentioned earlier, we only had attributes because we were checking for the extract all and the extract functions. So all of the nodes that we needed to visit were attribute types, which meant that when we actually hit an attribute node, we could then perform our checks, and that's all we had to do from there. All right, so let's go ahead and let's actually walk through the code. I'm going to apologize. There's a lot of code. I split it into 2 slides, but it's still going to be fairly small. But don't worry, I highlighted everything for you, so you should still be able to see. All right. So you might have noticed here we have the extract all. So this is already within that overridden function for the attribute node. So we're already assuming that node is going to be of type attribute. So we have .attr for checking here. So as you can see here, the first thing that we do is we check to see if the attribute is extract all. So as I mentioned earlier, one of the things Bandit did was you had to actually look for a specific node and then go down. So if we had done this with Bandit, we would have actually had to check for the with block and then go down, try to find the attribute node within the with block, and then there's a lot more with blocks that use open than there are just nodes that call extract all, because it is really, just for extraction. Once we have that, you can see here, we check to see if the parent's parent, I know it's a lot of parents, but that's just because of how it's nested. That is always going to be that way if it's in the indentation, so you don't have to worry too much about things changing, which is pretty nice. But we check to see if it is a with block, and then we go through, and here you can see that we check to see if that with block contains an open function. And the reason we check to see if it contains an open function is because that was kind of the template that we saw for this vulnerability a lot of times, and we want to make sure that the file was actually opened there and it's not just an extract all that might have been something else. Once we see that there is a open function, we go through and we check to see if the the second argument in there is going to be R. The reason we check the second argument, not the first, is because the first is always going to be your file, and then the second is going to be if it's read mode, write mode, all of that. So we check to see if it's R. However, we also check to see if there are no arguments, because we have the R is actually setting mode, which is an optional parameter, which means that it might actually be set directly with mode. And so we do a check here as well to see if mode is set to R. And then there's later on another check to see if the variable isn't set at all. So if args is not set at all on the second one, that means it's automatically defaulting to read as well. And then here we have our extract check. And as you can see here, we have extract, where we check to see if it's extract. However, you see that we do a lot more checking here as well. Also, don't worry, these slides are all online and the code is public as well, so if you can't read the slides here, the code is available. It's all commented exactly the same. Don't worry, I didn't publish code without commenting. That would be a little bit cruel. But anyways, so here we check to see if the actual node for the attribute class is also a call function. And then because the extract function has to be an actual call, otherwise you can't extract. But then we check to see if it actually has parameters, because there are a lot of other extract functions out there, and a lot of them will just extract the object that they're attributed to rather than have something passed in. However, with the Python tar file module, you do actually need to have an object passed in, so that's why we perform a check here to make sure that there is actually an object before we do other checking, which cuts out most of the false positives in the checks here. Then we go through, and again, the parent, and we check to see if that is a for loop. Because the extract vulnerability, that templated vulnerability we saw, was within the for loop. And then once we do that, we have another check here to make sure get members is in the for loop. Now, a lot of you might be noticing that I stopped using abstract syntax trees here for this section, especially the get members. And you might see that I have ast.unparse. And the reason for that is because for loops can get pretty complicated pretty quickly, and things can be set differently. You can assign multiple items at once. However, Python's abstract syntax tree has a .unparse function which takes whatever node you have and only that node and then transforms it back into source code. And what we can then do is, rather than trying to traverse that node and going down, we can just directly do a string check to see if the get members function is in there, which actually sped it up a lot, which was nice. We then later on use that and see if we have R in open, and then we do another check as well. So you can probably see we have a bucket where if R is in that string, we attach it to vulns, otherwise we attach it to probable vulns. And the reason for that is if there exists an open function in a for loop and you don't see R specifically, it's most likely still going to be opening for read mode. And it can either be that the variable isn't assigned or the variable mode is directly assigned via a parameter as well, because it doesn't have to be set directly to an R. The parameter can be set to, or the argument can be set to R and then passed through later on. So now that we've talked about how we actually detect the vulnerability, especially over all those lines of code, let's actually talk about how our confidence levels are set up. So as I mentioned earlier, our confidence levels are used to determine which lines need priority during the checking process. Because you only want to really check something if it's really vulnerable. And if you were paying attention to the code earlier, you might have noticed that we have 3 different categorizations for this. The first categorization is vulnerable. Next we have probably vulnerable. And finally we have potentially vulnerable, which I know aren't the most descriptive. So I was trying to make an internal tool that would check ours, and then we ended up publishing it because it was working. So let's actually go through and explain how those work. Anything that's marked as vulnerable, especially if you're scanning your own code base, you definitely need to check out. Anything marked as vulnerable is pretty much guaranteed to be vulnerable. There's a few small cases where that's not the case, which I'll discuss later, but for the most part, you need to check it. Anything marked as probably vulnerable is something that had all the specifications for vulnerable, but had some sort of modification. So in the last slide, I showed you how if it doesn't have open and R, it went from vulnerable to probably vulnerable. And that's because it most likely still is vulnerable, however, we can't guarantee it. And we didn't want to do patching on anything that we couldn't guarantee that was vulnerable. So anything marked probably vulnerable still, most likely is vulnerable. And then finally, we have our catch-all, which is potentially vulnerable. And the reason why we added this bracket was if there was an extract all or an extract, we still wanted to add it to potentially vulnerable because we were checking our own internal code and we wanted to make sure that there were no vulnerabilities in our own code bases. All right, so now that I've talked about the tool, let's actually talk about how the finding summarization is done. Since I mentioned we need some way to detect the vulnerabilities, we need some way to show confidence levels, and then we need some way to actually show the vulnerability. So this is actually a live result from URH, which is Universal Radio Hacker. This has already been disclosed, and we have a blog post that was originally released when we discovered the vulnerability. Since then, we have a lot of updated information since the patching process started in September, but actually finished about 2 weeks ago because of the large amount of patching we had to do. So if you are curious about how we actually exploited URH using the Python vulnerability, you can read the blog post. You can just Google Trellix tar file, and you'll most likely be able to find it. Anyway, so let's go through and actually discuss what you see here. So as you can see, Creosote gives us a nice summary up top telling us how many files had vulnerabilities. It then gives us an overview of how many vulnerabilities it found, how many probable vulnerabilities it found, and how many potential vulnerabilities it found. What we then also have is we have it going through every single file, giving us the full path to the file that's vulnerable, as well as telling us how many vulnerabilities it found and what line numbers it found. So on file operator, we can see that we have a vulnerability on line 224. So you would go to that file, line 224, and that's actually where you would find the vulnerability from back then. It's been patched by now. The way that Creosote works, if there's multiple vulnerabilities in a file, it will just do a comma-separated list rather than just saying found vulns on line and keep going, because that would be pretty annoying over a course of time. All right, so obviously we can do stuff better. I was writing this tool by myself. I was writing it pretty quickly, and it was not meant to be scalable. It was meant for this one specific purpose. And there's other tools that are already scalable. Those exist. I'm not going to try to write a tool that everyone can use for everything it wasn't intended for. However, there are still lessons to be learned. I'm not perfect. I didn't know everything. I learned a lot during this process. The first was that I definitely needed to have better finding summarization. So it worked for what it needed to be. but especially when I started going through the potential vulnerabilities, it got pretty tedious pretty quickly going through and actually checking every single file. So one of the things that I thought I could add better here was add a context in the summarization. So you add the vulnerable line of code, and then you also give context of 2 lines before, 2 lines after, or something like that, just so you can go through really quickly in the report and say, oh, that's definitely not vulnerable. That's not even the tar file module. Or you can actually go through and see, hey, that might be vulnerable. Let me check it out. Another thing that I thought might be pretty useful is you can add hot links for the numbers. So especially depending on your development environment, you can pretty quickly, code up something where if you have a number, you press it and immediately takes you to the exact line of code in the exact file, opens it up, everything for you, which would be very useful, especially if you're combing through a lot of these. I also thought it would be nice to add object tracking, especially through functions. I've done a lot of work with abstract syntax trees in the past, especially with deobfuscation, and one of the things I worked on there was actually tracking objects as they're passed through functions. As I mentioned earlier, sometimes you have arguments that are then used, and what you can do potentially is you can track back through the functions all the calls that go to that function, and then see if any of those are set to R, possibly create import chains that directly tell you where the vulnerability starts and then where it ends up. And then we also want to add more checks to bring some of those potentially vulnerable to possibly vulnerable or vulnerable, because we did make a fair generalization because a lot of the vulnerabilities were the exact same vulnerability. However, you can definitely add a lot more checks and find more with a higher accuracy. And then finally, what would also be nice would be to add a way to analyze better what happens between the open and the extraction of the actual file. And as I mentioned, most of the vulnerable ones were vulnerable. However, there were rare cases where they actually performed some sort of check on the file between the open and extraction. This was less than 1% of the files that we saw, because any ones that actually did checks, they did it during the extract all process. So that's why we checked that extract all didn't actually have anything special there, because when you do extract all, you can specify which members to extract. So what they normally do in the extract all is they set the members to some sort of function that then goes through and checks the members and then passes them in, which is actually what we do in our patch. So now that we know what we can do better, we've talked about the tool, let's actually talk about the real meat of what's happened since September and now, which is patching by the thousands, or actually tens of thousands. So the first question is, why did we decide to patch? It's a pretty big amount of work, and we had a lot of people get pretty angry with us, especially small repo owners. Why are you spamming us? Stuff like that. And the first reason was we wanted to raise awareness about the issue. This issue had first been discovered in 2007 and had pretty much been forgotten about by the community, as you can see by all the tutorials that show you how to incorrectly do it. As I mentioned earlier, Python didn't even know whether or not they wanted to patch the issue. And the reason for that was because they wanted to remain compliant with the actual specifications of the tar archive. Since the tar archive does allow you to do path traversal, they wanted to make sure that they didn't change anything and break stuff, which I'll talk about later as well. So we saw that an upstream patch was likely to be delayed, which is not good considering that 61% of the projects that we hand-checked were vulnerable to the tar file extraction. So for the ones that we checked, I went through and I personally checked every single Python project on GitHub over 5,000 stars. And of all the ones that imported the tar file module, 61% of those were vulnerable to the extraction, which is not great, especially considering what a lot of those projects have or are used for. So now that we've talked about why we decided to patch, let's talk about what to patch. So we decided that we wanted to only patch the extract all in the with block, because while the extract in the for loop was pretty common, the extract all did represent about 80% of the vulnerabilities that were out there. So, as I said, 80%. And then we only wanted to patch what was actually vulnerable. Nobody wants a bunch of pull requests to something that's not vulnerable, or not even the tar file module, right? So what you actually see here above is the actual patch that I wrote. So this patch is, I took some of the code and was inspired by the pip module, or not the pip module, but pip, the source code, where they actually do it correctly because they know it's an issue and decided to fix it. Especially since if you've ever, cloned something, or not cloned, but used pip It's all tar archives, which is a lot of fun. And the way that it works is you see here we run absolute path on the directory we're trying to extract into and an absolute path on the file we're trying to extract. And what that gives us is it gives us a common prefix, so we know where it's trying to go. And the reason why I did it like this was because I knew I was going to make mistakes, and I knew if I was trying to make a filter, somebody would come up with some insane way to bypass that filter. And then another reason why we did this was because we listened to Python, we listened to the community, and I wanted to make a way where you still had path traversal, especially within the directory that you want to go into, but it was still secure in the fact that it did not go outside of where you wanted it to go to. So if you did want path traversal, you could just do root, and you'd still be able to use it exactly how you were planning on using it. All right, so now let's actually talk about applying the code patch. So there's two main ways that you can apply a code patch. The first is abstract syntax trees, and the second is just source code patching, at least for this project. However, both have some drawbacks. So while abstract syntax trees allow you to actually replace nodes fairly easily, it can be pretty inefficient because whenever you create a new node or replace a node, you have to re-index a lot of things as well as add information. And the second main drawback is that you have to convert the tree back to source code. And there are a lot of tools that do that. However, every time you convert something back, it does it in exactly the format that the source code converter did. So that means all the formatting that's already in the file is going to be gone, and it's actually going to modify the entire file rather than just what we wanted to patch, which means it's very annoying when you're trying to go through and figure out what was changed for a merge. And it can also mess up whatever conventions they have. The second approach I mentioned was actually modifying the source code directly, which means you have to start parsing a lot of things. And that can get pretty tedious pretty quickly, especially since everything has different ways that it's set up. Another issue is we're working in Python, and you have to worry about indentation, which is lovely, especially spaces versus tabs, and that just becomes a mess. So what I decided to do was leverage abstract syntax trees to actually apply the code patches. So we were able to actually pull a lot of the information directly from the abstract syntax trees nodes. So we got the line number from the node. We were able to get the variable names, the parameters and arguments, all of those from the different nodes that we already had in our memory that we were using to check for the vulnerability. And we were also able to pull the indentation from the abstract syntax tree node. And then finally, once all the data was grabbed, we were able to rewrite the code directly. Since we knew the line number, we could just remove the line, take our code patch, apply all their parameters, all their indentation, and then paste it directly into the code without modifying any of the other files. So obviously, we had issues. Former developer, so I'm used to these. Some of these were quite surprising. The first was there were actually so many files that contained the tar file module that GitHub was not able to use their new search functionality to get those files for us. And they actually had to go through and comb through a bunch of old data sets to figure out which files contained the tar file module, which was a lot of fun for them and for us, and they told us a few stories about that. And obviously, some of those repositories didn't exist anymore. So when we were trying to clone or do forking and all that, things broke. Of course, there's also edge cases that you never expect. I had a pretty large batch running, and I woke up in the morning to everything having completely crashed and having lost the entire night. And that was because a developer decided to put an emoji in a file name, and I had not anticipated that at all because, who would? And then obviously speed issues. So I mentioned Creosote was originally written just for finding the vulnerabilities. So we had quite a few speed issues that required optimizations, but if any of you have ever written tools, optimization is really the fun part, especially seeing the numbers go down. And then finally, we had hard drive space issues. And the reason for that is because we had around 350,000 of those 600,000 repositories that contained the tar file module were actually vulnerable. So a lot of them weren't truly vulnerable, so we only had to, and it was a small number that we actually had to locally save off, but we wanted to make sure that all the patches were done locally and saved locally so we could audit them before we start, annoying everyone with a ton of pull requests that are wrong. And storing, 60, 70,000 repositories takes up quite a bit of space. I will talk about how we solved that in a minute, though. So solving the speed issues. As you can see here, there's quite an overhead to even get the first file. And the reason for that is because when you're iterating over millions of files, it takes some time to sort through those files. When we first used Creosote, it was actually using glob rather than iglob, and glob goes through and collects all the files. However, it has to load them all into memory first. So when you have that many files, it takes a while to load into memory. iglob, however, is a generator, so it runs asynchronously, and we were able to, as you can see, basically instantly get the files. We also did some changes with in-memory versus file I/O. So rather than reading the file each time from the file system, we stored it in memory and passed it along. And then originally, as I'd mentioned earlier with Creosote, we go through the stages, find all the files, then find which ones have tar file. We changed it so that it would go through all the files, find a Python file. If it had tar file, we would immediately check it and patch it, which not only sped it up, but what it also did was it allowed us to if something did crash, like with the emojis, we didn't have to restart the entire process. Thank you. So we went from about 300 seconds for just to even start to about instantaneous, and then we went from about 5 to 6 seconds per file to around 2 seconds per file, which was a pretty good speed up. So as I mentioned, we also had the disk space issue. So what I decided to do was I created this new way to actually store the patches. So we have our patch directory, which has all our patches. We have a directory number. The reason for that was because a lot of the repositories had similar names, so it was pretty hard to have some way to do that. So we just indexed all of them and then referenced them later. We also have matches.txt, which looks like this. There's just a separation that I put in there, which would hopefully never show up in a repository name. We went through a few of those, as you can probably guess. And then there is the relative path to the file in the repository, and then the unique ID. And you can see that we have the original folder and the patch folder, and both of them have a file with that unique ID. And the reason for that was because we saved off the patch file and the original file. And the reason we did that was because when we were doing our forking, we checked to make sure the original file had not changed since we did our patch. And we did that because we didn't want to regress the file that we were merging into, because that would really just annoy a bunch of developers. So now that I've talked about how the patches work, let's actually talk about doing all this in scale. So we had a fairly automated process. There were 6 major steps, which you can read, and those were split into 2 components. We had cloning, patching, and saving, and then forking, committing patches, and then pushing and doing pull requests. The first 3 steps were done on one side, so that was all done offline. So we cloned all the repositories, we patched them, and we saved them locally in the setup that I just told you about. And then after that, we went through and we did everything later. For a few reasons. 1, so we could audit, and 2, so we weren't just patching a bunch of random repositories without actually having told the world that this is an issue, because then people might see it and start going to other things. So let's actually go through and run through the code for each of these components. And I tried being nice and making snippets of code that were nice and small, so you had a little bit more text. So this is the first snippet. This is to actually clone the repo. You can also see we have an insert auth here. And what we do here is we take the authentication token, which I was luckily smart enough to remember to X out. Otherwise, you would have all seen our authentication token, which wouldn't have been great. We have our GitHub username, and then auth is just a string combining those two. Insert auth puts them into something you can use. And then in clone repo, we have clone from, which luckily enough, there is a pip module named git, which actually does cloning for you, which is great. And then you can see that we return the object that returns at the end there. Next, we have fork repo, which actually uses the object from the clone repo. This is just a string name, sorry. But the first thing that we do is we add a random component to the repository name. As I mentioned earlier, we do have a lot of repeats in repository names, so we added 4 random characters to the end so that we didn't have overlap. And since in the end we had an estimate of 60 to 70,000 that were truly vulnerable and trying to patch, we figured that 4 characters would be enough because we didn't want to add a ton and have a ton of overhead. Then in the headers, we add our authentication token. And then we have our JSON object, which is just the new name in the name field. And then we actually have to use requests directly to send that. So we had to reverse GitHub a little bit. It's not too hard because you can just use developer tools, luckily. But for this, there is no library that actually does the work for you, so you do have to directly do the requests. Next, we have our committing and our pushing. Committing is nice and simple because you can once again use the git pip module. Here you just add your name, you add your email, you add all the files or whatever files you want to add. We added them all since we actually wanted all the files we modified to be there. And then you go through and you commit. Our commit message was just saved off at the top of the file just to make the code a bit neater. And then pushing is pretty similar. You have the remote branch, and then you actually just do git push, which is really nice and simple. And then, oh, there we go. And then finally, we have creating the PR. So creating the PR, we once again had to reverse how GitHub does it a little bit and do requests directly. So up here, what we do is we grab the prefix and just split it out to get the name. Here, we once again add the authentication token to the headers. And then here we add the data to our request. The two important components that you have to look at are title and body. So for the title, it's obviously whatever title you want for the PR. However, body is important because body is actually the markdown body of the pull request. So when you go on GitHub and you see the long list, that's actually going to be what gets populated by body here. So you do have to make sure that whatever you have in there can actually be passed in as a string and is marked down. And then finally, we just do a simple post request, which goes through and does the request, and that's how we did the pull request. So now finally, let's actually talk about the results of all this. It finished about 2 weeks ago. Trellix is releasing a blog post on Monday if you are interested in reading more about the whole process and the results of that, but I'm gonna give you a quick overview. In the end, we were able to send out 61,895 pull requests. This took about 3 months to do, so it was a lot of fun. We did have some pushback. However, we had a lot of notable projects actually accept the pull request and actually thank us. So I'm just going to go through and talk about some of those projects real quick. The first one, which I definitely am most proud of, is MobSF. Most of you, or a lot of you, if you've ever worked with Android, you've probably used this tool since it's an amazing tool, security tool for analyzing Android, just anything Android. And they actually merged our pull request and sent us a thank you message. We also had Open3D Engine, which is the largest open source game engine, accept our pull request as well. And we had a few people from Amazon, since there's a few Amazon people actively working on it, send us thank you messages as well. And then another notable one is MonAI, which most of you probably don't know. However, it is a medical open network for artificial intelligence. And what's really notable about this diverse group is we really impacted every single industry. You have security, you have gaming, you have medical and AI, and all of these were impacted by this Python vulnerability. We also had a few people who didn't want to merge our pull request directly, but instead contacted us and asked us to check if the changes they had done were truly secure. One of the most notable ones and a group that was actually very fun to work with was Conda. So Conda, thanks to our pull request, found that their package streaming was vulnerable to the tar file. And with package streaming, that's a bit remote. So that's not great if it can be remotely accessed. So we were able to work with them and patch that as well. Thank you so much. This was my first talk at a major conference, so thank you so much for coming. If you have any questions, now's the time. Yes. Yeah. Yes, so he just asked, after we had scanned and everything, how we went from having it locally to actually going through and doing the pull requests. So the way that that worked is we just had a little bit of code that recloned the repo, which is why it took so long. So it cloned the repo, checked to see if the original file was still the same, which there's tons of different ways to do that. We just did a text comparison because we wanted to make sure nothing got wrong with hashing. And then we just overrode the file and then did our commit and pull request. So it's just a nice, simple process. Yes?
Have you guys updated all the tutorials yet?
So he asked if we've updated all the tutorials. Sadly, no. We have, this is why we did it. People are talking about it. I've talked to a few people at the conference and they actually, said, hey, I actually read your blog post, which is a great feeling. So hopefully we can get this updated, but no, as of now, I don't think they're updated. Yes? No worries. I'll answer the first one first. So he asked if Python has responded and actually, fixed it or started fixing it. We actually worked with Python when we first released the research. I was talking with them. I showed them. I sent them my patch. I was explaining how the patch worked and all of that. There was discussion for a few months. However, the discussion has pretty much died down once again. So it is actually still in Python's tar file module. And the discussion really went from, started with how are we going to patch this to back to are we even going to patch this? Because it's, it is valid. You can use tar files that way. So right now the discussion pretty much has died down. Did you remember your second question? All right, I have to stop, but if anybody wants to come up to me afterwards, I'll be here for a few minutes, so if you want to come talk, I'll be here. Thank you so much again.